A small earthquake in Alaska barely shook the surface, but for scientists, its location matters far more than its size. Beneath the frozen coast, one of Earth's most powerful plate boundaries is slowly storing stress. Most small quakes fade into the background, but sometimes a tiny tremor appears in exactly the kind of place researchers watch closely. It is not a prediction. It is not panic. It is a quiet signal from deep rock, where pressure builds over years, decades, and centuries. In this video, the journey moves beneath Alaska's mountains, coastlines, faults, and sinking plates to understand why one small quake can raise much larger questions. If calm science documentaries help the channel grow, please like this video, subscribe, and stay with the story. Alaska rests at the far northwestern edge of North America, broad and cold, with mountains, forests, rivers, tundra, glaciers, bays, and dark ocean water spread across a region larger than many countries. From a wide view, it appears quiet. Snow lies on high ridges. Ice fields hold their pale surfaces in valleys. Long rivers bend through lowlands and empty toward distant seas. The land seems still because most motion is too slow for ordinary sight. Yet beneath that still surface, Alaska is one of the most active earthquake regions on Earth. The ground carries the long memory of moving plates, lifted mountains, sinking basins, and faults that cross both land and sea. A small earthquake in Alaska may pass almost unnoticed by people at the surface. It may shake a few instruments, loosen a little snow, move a hanging lamp, or leave no visible sign at all. Its size may be modest compared with the great earthquakes that have shaped the region in the past. Still, scientists pay attention to small earthquakes because they reveal where the crust is adjusting. The crust is Earth's thin outer rock shell, and in Alaska it is under steady pressure from large tectonic motions. Tectonic plates are broad-moving slabs of Earth's outer layer. Their movement is slow, usually only several centimeters each year, but over time it builds mountains, opens cracks, and produces earthquakes. The surface of Alaska gives many calm clues to this deeper movement. The highest parts of the Alaska Range rise in sharp lines, with slopes carved by ice and weather. Denali stands above the surrounding land as part of a mountain system shaped by compression, uplift, and erosion. Farther south, the Chugach Mountains and coastal ranges rise near the Gulf of Alaska, where ocean air carries moisture inland and feeds snowfields and glaciers. Farther west, the Aleutian Islands curve into the northern Pacific, a chain of volcanic landforms marking one of the most important plate boundaries on the planet. These features do not form by sudden events alone. They form through repeated motion, steady pressure, and long intervals of quiet change. A small quake becomes meaningful in this setting because it is not isolated from the surrounding land. It belongs to a wider pattern. Seismic instruments across Alaska record many earthquakes each year, from tiny tremors too small to be felt to larger events that can damage buildings and change coastlines. The word seismic refers to shaking or waves caused by motion in Earth. These waves pass through rock after a fault slips. A fault is a break or weak zone in rock where one side can move past another. When the motion is small, the earthquake may release only a limited amount of energy. When the motion is large, the same process can affect a broad region. The quiet surface of Alaska hides several kinds of earthquake sources. Some earthquakes begin near the coast, where the oceanic plate pushes beneath the edge of the continent. Some begin inland along long crustal faults, where blocks of rock shift sideways or upward. Others occur deeper beneath the land, inside a descending plate as it bends and sinks. At the surface, these different sources may all appear as shaking, but instruments can separate them by depth, location, and wave pattern. A small event can therefore raise concern not because of its size alone, but because of where it happens, how it fits with nearby events, and whether it occurs in a region known to store strain. Strain is the slow change in shape that builds in rock when force acts on it. Rock can hold strain for a long time. It can bend slightly, compress, stretch, or shear, even though it feels solid and unchanging at human scale. When the built-up strain becomes greater than the strength of a fault patch, the rock slips. The stored energy travels outward as seismic waves. In a small quake, the slipped patch may be short and the motion may be slight, yet its position can show that a fault is active. It can also show how stress is moving through the crust after previous events. Alaska's surface also carries the marks of past large earthquakes. In some coastal areas, land has risen or dropped during powerful ruptures. Trees have been drowned by sudden lowering of ground near saltwater. Shorelines have shifted. Marine terraces and uplifted rock show repeated movement through time. These signs give scientists a broader context for present activity. A small earthquake today is measured against that longer record. It is not treated as a prediction by itself. Modern earthquake science does not provide exact forecasts of the time, place, and size of future earthquakes. Observations indicate where strain is accumulating and where faults are active. It remains uncertain when a particular locked section will break. Across the wide Alaska landscape, scientific concern often means careful attention rather than alarm. A small quake can lead researchers to examine instrument records, compare aftershocks, update maps, and look for small changes in ground motion. Satellite measurements can show whether land is slowly shifting. Global navigation satellite systems can measure steady movement of stations fixed to the ground. Seismometers can detect waves passing through rock. Together, these tools help scientists understand how the region breathes in a very slow geological sense, with some areas being compressed, some being stretched, and others moving sideways along faults. The calm outer setting remains important because earthquakes are part of the whole landscape, not separate from it. Ice, mountains, rivers, forests, towns, roads, pipelines, and coastlines all occupy a land that continues to adjust. Most small earthquakes cause no damage, and many are useful as natural signals. They illuminate buried structures in the same way that faint light can reveal the outline of a room. The land above them may remain quiet, with snow on the ridges and clouds over the sea, while below, rock records pressure and release. In Alaska, even a small tremor can become a point of interest because it appears within a region where Earth's surface is still being built, pressed, broken, and lifted, slowly and continuously, beneath a wide and silent northern sky. Alaska's coastal margins form a long meeting place between land and ocean, where the edge of North America faces the cold northern Pacific and the Bering Sea. The coast is not a simple line. It bends around bays, fjords, islands, peninsulas, river mouths, tidal flats, cliffs, and glacial valleys. Some stretches are low and marshy, with broad wetlands that rise only gently above the water. Other stretches are steep, with mountains dropping close to the shore. The sea moves against these margins through tides, storms, currents, waves, and seasonal ice. The land beside it moves more slowly, lifted or lowered by tectonic force, pressed by glaciers, and shaped by erosion. Along southern Alaska, the coastline lies near one of the most active tectonic boundaries on Earth. This does not mean the surface is always shaking in a way people feel. It means the region is part of a large system where plates continue to move, and where stored strain is released in earthquakes of many sizes. The coast is important because it often sits above or near the zone where the oceanic plate descends beneath the continent. That descent is called subduction, a process in which one tectonic plate moves beneath another and sinks into the mantle. At the surface, subduction may be marked by deep ocean trenches, volcanic arcs, mountain belts, and frequent earthquakes. The Gulf of Alaska is a broad body of water south of the mainland, open to strong weather and long ocean waves. Moist air moves from the ocean toward the mountains, rises, cools, and drops snow and rain. This climate feeds glaciers that flow from inland ice fields toward the coast. Glaciers scrape valleys, carry broken rock, and change the weight placed on the crust. When ice grows or melts, the crust responds slowly. This response can influence local stress, though it is only one part of a much larger tectonic setting. Scientists consider these surface loads carefully, especially in places where glaciers have retreated and the land continues to rise. In many coastal areas, the ground records earlier movement in quiet, visible forms. Raised shorelines show where land has lifted relative to the sea. Sunken forests show where land has dropped, and salt water has entered areas that once supported trees. Layers of sand carried inland by old tsunami waves can remain buried in marshes. A tsunami is a series of long sea waves caused by sudden displacement of water, often from large earthquakes beneath the ocean floor. These layers do not speak by themselves, but when studied with careful dating and mapping, they help scientists reconstruct past earthquakes along the coast. The coastal margin also holds towns, harbours, roads, small airstrips, fishing grounds, and cultural places that have long histories. Communities live with the ocean's movement and the land's movement at the same time. Earthquake science in this region is therefore not only about distant rock, it also concerns practical understanding of shaking, landslides, coastal change, and tsunami risk. A small earthquake near the coast may draw attention if it occurs close to a known fault, or near a segment that has produced larger events in the past. Its meaning depends on depth, location, mechanism, and relation to nearby activity. A mechanism describes how the fault moves during an earthquake, such as sideways, upward, downward, or a combination of motions. Coastal Alaska is also shaped by the difference between steady motion and sudden motion. Global navigation satellite systems show that parts of the coast move by small amounts each year. Some places shift horizontally as plates converge. Some places rise as ice mass changes or as the crust responds to deeper forces. Other places are pulled downward when a locked plate boundary drags the edge of the continent with it. These motions are slow and usually measured in millimeters or centimeters each year. They are small in daily life, but they accumulate through decades and centuries. When a locked zone finally slips, sudden coastal uplift or subsidence can occur. Small earthquakes near the coast can help outline which parts of this system are moving freely and which parts may be storing strain. They do not give a simple answer. Many small earthquakes happen in active regions without leading to larger events. Some occur as aftershocks after a previous rupture. Some are background activity in a restless crust. Scientists use them as pieces of evidence, not as direct warnings by themselves. Observations indicate that clusters, depths, and fault motions can reveal changes in stress. It remains uncertain how any single small event relates to future larger rupture unless it is placed within a wider pattern. The coastline itself responds to earthquakes in several ways. Strong shaking can loosen slopes above fjords and bays, sending rock or sediment downward. underwater landslides can disturb water and, in some settings, create local waves. Soft sediments near river mouths can shake more strongly than hard bedrock because loose grains may amplify motion. In wet, sandy ground, strong shaking can sometimes cause liquefaction, a process in which water pressure rises between grains and the ground temporarily loses strength. These effects depend on local conditions. A small earthquake usually does not produce them, but understanding the coastal surface helps scientists and planners prepare for stronger shaking when it occurs. The outer coastal region therefore becomes a natural record keeper. It receives the signals of the ocean, the ice, the weather, and the moving plates. It shows old changes in marsh layers, rock terraces, drowned trees, and uplifted beaches. It also holds modern instruments that measure motions too slight for direct sight. When a small Alaska quake raises concern, the coast is one of the first broad regions scientists consider. They look at whether the event lies near the shore or offshore, whether it aligns with known structures, and whether it belongs to a pattern of stress along the margin. The view remains calm and measured. Waves continue to arrive. Tides continue to rise and fall. Glaciers continue to move slowly toward the sea or retreat into valleys. Beneath this changing but steady coastal surface, the rock edge of a continent continues to answer the pressure of an oceanic plate. South of Alaska's coastal mountains, the offshore seafloor stretches beneath cold, dark water, carrying the surface expression of a plate boundary that cannot be seen directly from land. The sea above it may appear open and empty, with waves crossing long distances and storms moving across the Gulf of Alaska. Beneath that water, the ocean floor is not flat in any simple way. It holds slopes, ridges, basins, sediment layers, submarine channels, and the long trench region where one tectonic plate begins its downward path. The seafloor is a broad outer shell over deeper motion, and it records both the slow travel of the Pacific plate and the pressure it brings toward North America. The Pacific plate moves generally northwestward in this region, carrying oceanic crust that formed far from Alaska at spreading centers where new seafloor was created. Oceanic crust is thinner and denser than continental crust. It is made mostly of dark volcanic rock, covered in many places by sediments that settle slowly through the water or are carried from land by rivers, glaciers, and underwater flows. As the plate approaches Alaska, it does not simply stop at the continental edge. It bends and begins to descend beneath the margin. This bending creates stress within the plate and changes the shape of the seafloor above it. The offshore region is therefore important for understanding even a small earthquake. A modest event located beneath the ocean may occur on or near the plate boundary, within the bending oceanic plate, within sediments above the boundary, or within faults that cut the outer slope. Each setting has a different meaning. Scientists determine location and depth from seismic waves recorded by instruments on land and, where available, by ocean instruments. A shallow offshore earthquake may be close to the interface between plates, while a deeper one may occur within the descending slab. The word slab refers to the part of a plate that has begun to sink beneath another plate. Sediment on the seafloor plays a quiet but significant role in this outer region. Glaciers grind rock on land and carry fine material toward the coast. Rivers and meltwater move sediment into bays and the open ocean. Storms and gravity can shift this material downslope. Over time, layers of mud, sand, and broken rock gather on the ocean floor. Some sediment is scraped off as the oceanic plate descends, forming a wedge of deformed material near the margin. Some sediment may be carried down with the plate. These layers can affect how faults slip because water-rich sediment may be weak, while compacted rock may be stronger. The seafloor also holds evidence of past sudden movement. In some basins, layers disturbed by shaking can show where sediment slid or settled rapidly. Underwater landslides may leave scarps and deposits. A scarp is a steep step or slope formed by faulting or mass movement. Scientists study these features with sonar, cores, and seismic imaging. Sonar maps the shape of the seafloor by sending sound waves through water and measuring their return. Seismic imaging uses waves to outline layers beneath the bottom. These methods do not remove uncertainty, but they help connect present earthquakes with older changes preserved offshore. The offshore plate boundary is part of the larger Alaska Aleutian subduction zone. A subduction zone is not a single thin line. It is a wide region where the descending oceanic plate, the overriding plate, sediments, fluids, faults, and bending stresses interact. The actual contact between plates lies beneath sediment and rock, dipping downward from the trench toward the land. Some parts of this contact may creep slowly, releasing strain without large earthquakes. Other parts may lock, allowing strain to build. Small earthquakes near this region can help mark changes, but they do not by themselves show whether a larger rupture is close. In the water above the seafloor, nothing may show the difference between a locked area and a creeping one. The ocean surface may remain calm under a grey sky while instruments record tiny shifts below. This contrast is important in earthquake science. The most important motion can be hidden. Scientists rely on indirect evidence, including earthquake locations, waveforms, seafloor shape, sediment records, and precise ground motion on nearby land. Offshore measurements are more difficult than measurements on land because instruments must survive pressure, corrosion, currents, and limited access. For that reason, uncertainty is often greater beneath the ocean than beneath well-instrumented land. The shape of the offshore seafloor can also influence tsunami hazards when larger earthquakes occur. If the seafloor moves upward or downward suddenly over a broad area, it can displace water. The water then spreads outward as long waves. A small earthquake does not usually move enough seafloor to create a damaging tsunami, but its location may still matter if it occurs in a region known for larger ruptures. Scientists separate immediate hazard from long-term concern. Immediate hazard depends on event size, depth, seafloor displacement, and observations from sea-level instruments. Long-term concern depends on the structure and history of the plate boundary. The offshore region is also crossed by faults that respond to the bending of the Pacific plate before it descends. As the plate curves downward, its upper part may stretch and crack. These outer-rise faults can produce earthquakes seaward of the main subduction contact. Some are normal faults, where one block moves downward relative to another as rock is pulled apart. Such earthquakes can reveal how the plate is being prepared for descent. They also allow seawater to enter cracks, changing the physical and chemical state of the slab before it sinks more deeply. This process remains an active area of study, especially where fluids influence deeper earthquakes and melting. At the scale of the offshore seafloor, a small Alaska quake becomes one point in a wide hidden map. It may sit among older events, along a known trend, or near a boundary between different behaviors. Scientists examine its depth, its wave pattern, and its relation to the trench and coast. The seafloor itself remains unseen by ordinary eyes, but it is not silent. It has shape, layers, cracks, and records of movement. Above it, the ocean continues to move with tides and weather. Below it, the Pacific plate continues its slow approach and descent. The small quake becomes part of the steady record of how the ocean floor meets the continent, how stress is carried inward, and how the outermost hidden region of Alaska's earthquake system continues to change in increments too small for the surface to display. The Aleutian Arc curves westward from mainland Alaska across the northern Pacific, forming a long chain of islands that marks the surface trace of deep tectonic motion. From above, the arc appears as a narrow sweep between the open ocean and the Bering Sea. Some islands are broad and mountainous, others are small, steep, and exposed to wind, cloud, and waves. Their shapes come from volcanoes, erosion, uplift, and repeated earthquakes. The arc is not only a line of land. It is the visible upper part of a much larger system, in which the Pacific Plate descends beneath the edge of North America and the smaller blocks that form the region. The islands stand in a harsh oceanic setting. Weather changes quickly. Fog often covers ridges and bays. Waves strike dark volcanic shorelines. Snow may remain on high slopes while lower ground holds grass, moss, and bare rock. Many volcanoes in the chain are active or potentially active, though activity varies from one center to another. A volcano is a place where molten rock, gas, and broken material can reach the surface. In the Aleutians, volcanoes form because the descending plate releases water and other fluids into warmer rock above it, helping that rock melt. The process is slow and deep, while the surface may remain quiet for long periods. The Aleutian Arc matters for a small Alaska earthquake because it follows the same broad tectonic boundary that produces much of the region's seismic activity. Earthquakes occur beneath and around the arc at many depths. Some are shallow and related to faults in the crust. Some occur on the plate boundary where plates press together. Others occur deeper within the descending slab. Their locations form a dipping pattern beneath the island chain, a pattern that helps scientists see the shape of the plate as it sinks. The arc is therefore both a volcanic chain and an earthquake belt, with each process linked to the same movement of plates. The curve of the arc reflects the geometry of the boundary. The Pacific Plate does not approach the margin at the same angle everywhere. Along different parts of the chain, motion may be more direct or more oblique. Oblique motion means that the plates converge at an angle, producing both compression and sideways movement. This can create complex fault patterns in the overriding crust. Some faults accommodate sideways shear, while others respond to squeezing or stretching. A small earthquake in such a setting may not represent the main plate contact. It may instead show how the upper plate adjusts to the shape and direction of the motion along the arc. The islands themselves are built mostly from volcanic rock, ash, lava flows, and deposits moved by water, ice, and gravity. Lava is molten rock that reaches the surface and cools. Ash is fine volcanic material blasted or carried into the air during eruptions. Over long times, these materials build cones, ridges, and layered slopes. Earthquakes can occur within this volcanic crust as rock cools, cracks, or responds to changing pressure. In some places, small earthquakes near volcanoes may be related to fluid movement or stress changes, but their meaning depends on local observations. Scientists do not assume eruption from a single small quake. They compare seismic activity with ground deformation, gas emissions, temperature changes, and other measurements. The arc also carries the record of great earthquakes. The Alaska Aleutian subduction zone has produced large ruptures in historical time, including events that changed coastlines and generated tsunamis. These large earthquakes occur when broad sections of the plate boundary slip. Their effects can extend far beyond the islands, across ocean basins and coastal communities, Yet between these rare large events, smaller earthquakes continue to happen. They are part of the normal release and transfer of stress within a complex plate boundary. Their patterns help researchers understand which parts of the margin are active, which parts are quiet, and where strain may be accumulating. Seismic stations on the islands are valuable because they sit close to earthquake sources that would otherwise be distant from instruments on the mainland. They record ground motion from local tremors, regional earthquakes, and volcanic unrest. Some stations operate in difficult conditions, with wind, ice, salt spray, and limited access. Their records help locate small events more accurately. A small quake that seems minor from far away can become more informative when nearby instruments capture its waves clearly. The first arriving waves, later waves, and their relative strength help reveal the event's depth and fault motion. The ark's outer surface also shows how land responds to repeated shaking and weather. Slopes may carry loose volcanic material that can move during strong earthquakes or heavy rain. Coastal cliffs may fail into the sea. Valleys may hold deposits from old lahars, which are flows of volcanic mud and debris. Glaciers on some volcanoes can interact with heat, melt water, and unstable slopes. These surface conditions do not make every small quake dangerous, but they shape the consequences of stronger events. Understanding them helps scientists separate the earthquake source from the landscape response. Along the Aleutian Arc, silence can be meaningful, but it is not simple. Some areas show many small earthquakes, while others show fewer. A quiet patch may be locked and storing strain, or it may be creeping without producing many detectable events, or it may be poorly observed because instruments are sparse. A busy patch may indicate active adjustment, aftershock activity, volcanic processes, or ordinary background seismicity. Observations indicate patterns, but interpretation remains careful. Scientists combine earthquake catalogues with geologic maps, satellite measurements, sea level records, and field studies to reduce uncertainty. The arc is therefore a calm but active threshold between the ocean plate and the continent. Its islands rise above water as weathered peaks and volcanic slopes, yet their arrangement speaks of a plate boundary far larger than the visible land. A small Alaska quake within or near this chain becomes one small motion in a long curved system. It may show how a fault responds to regional pressure. It may help outline the sinking plate. It may add to a cluster that scientists continue to watch. On the surface, clouds pass over the island summits, waves fold against dark rock, and the land holds its narrow place between two seas. Beneath that surface, the same slow convergence continues to shape the arc. One movement, one fracture, and one measured signal at a time. The subduction front lies farther inward than the island surface and farther downward than the visible coast. Where the oceanic plate begins its long descent beneath the margin, it is not a sharp line that can be touched or seen from the surface. It is a broad contact zone, covered by water, sediment, and broken rock, where the Pacific plate presses against the overriding plate. In this region, motion that appears slow and steady at the scale of years can become sudden at the scale of seconds when a patch of the boundary slips. This is the setting that gives many Alaska earthquakes their deeper meaning. At the outer edge of the subduction front, the Pacific plate bends. Its upper surface carries sediments, older volcanic rock, cracks filled with water, and minerals changed by long contact with seawater. As the plate approaches the margin, it begins to tilt downward. The bend is gentle on a map of the whole region, but for rock it creates stress. The top of the plate may stretch and fracture, while deeper parts may compress. These changes can produce earthquakes even before the plate reaches the main contact zone. They also prepare the plate for the conditions it meets as it sinks. The front itself is shaped by friction between two enormous bodies of rock. Friction is the resistance that acts when surfaces try to slide past one another. On a plate boundary, friction is not the same everywhere. Some patches may be rough and strong, some may be smoother or rich in weak minerals, some may slip slowly without producing strong shaking. Others may hold still for long periods while the plates continue to move. A small earthquake near this front can show where a limited patch briefly overcomes resistance and releases stored energy. The contact between the plates is often called the megathrust, when it's considered as the large fault capable of producing the greatest subduction earthquakes. The word megathrust refers to a very large thrust fault, where one block of crust is pushed over another along a gently dipping surface. In Alaska, the megathrust belongs to a long and complex system. It does not behave as one uniform surface. Its different sections can be locked, creeping, or transitional. A locked section is not truly motionless in an absolute sense. It is stuck relative to the steady movement around it, so strain gathers in nearby rock. This locked or partly locked behavior is why small earthquakes receive careful attention. A small event does not mean that a large earthquake is beginning. Most small events end quickly and remain small, yet the location of the event may show activity at the edge of a locked area, within a patch of changing stress, or along a boundary between different types of slip. Scientists examine whether the quake is shallow or deeper, whether its motion matches the plate interface, and whether similar events have appeared nearby. They also compare it with long-term ground motion measured on land. At the subduction front, sediments can be scraped, folded, and compressed. Some layers are pushed into ridges and wedges above the descending plate. Other layers are carried downward. Water trapped in sediment pores can affect how easily the plate boundary slips. Pore water is water held in tiny spaces between grains. If pressure rises within those spaces, it can reduce the effective grip between rock surfaces. Scientists study these effects through drilling, laboratory experiments, seismic imaging, and comparisons with earthquakes in many subduction zones. The front is also uneven along its length. Ridges, seamounts, and rough areas on the incoming Pacific plate may enter the boundary. A seamount is an underwater mountain, often volcanic in origin. When such features are carried toward a subduction zone, they can change stress locally. They may increase roughness, alter fluid pathways, or create patches that slip differently from surrounding areas. Observations from many margins indicate that incoming seafloor shape can influence earthquake behavior. It remains uncertain in many cases exactly how a buried feature affects a specific small quake, because the structure may be hidden beneath kilometers of rock and sediment. Seismic waves help reveal this hidden front. When an earthquake occurs, its waves travel through different materials at different speeds. Dense, cold oceanic plate transmits waves differently from warmer or more fractured rock above it. By measuring arrival times at many stations, scientists estimate where the quake begins. By studying wave shapes, they estimate how the fault moved. These estimates improve when instruments surround the source. But offshore Alaska remains difficult to observe in places. This means that some small earthquakes carry wider uncertainty in location and depth. The subduction front is not only a mechanical boundary, it is also a region where water and minerals begin a deeper transformation. As the Pacific plate descends, pressure and temperature increase. Minerals that formed near the seafloor become unstable under new conditions. Some release water into surrounding rock. At this front, the process is only beginning, and many changes remain gradual. The immediate concern for a small quake remains mechanical, involving stress, friction, and slip. Still, the presence of fluids can influence the strength of the boundary and the way seismic energy is released. In this region, concern among scientists is measured and specific. It does not come from a single small number on a magnitude scale. Magnitude describes the size of an earthquake based on the energy it releases. A modest magnitude can be common in Alaska. Concern comes from context the quake's place on the boundary, its depth, its mechanism, its relation to other events, and its position within the known history of the margin. If the event occurs near a segment that has been quiet, or near the edge of a previously ruptured area, it may invite closer analysis. This subduction front remains hidden beneath ocean and rock, but its motion shapes the surface far above. It is the place where slow plate convergence becomes stored strain, slow slip, small tremors, and occasionally large rupture. A small Alaska quake at this level is a brief adjustment on a vast contact. It does not speak alone. It is interpreted with nearby events, ground motion, seafloor structure, and the known physics of fault friction. Above it, the sea remains dark and moving. Along the coast, mountains and islands hold their visible forms. At the front itself, two plates continue their quiet pressure, and a small slip becomes one measured sign of how the boundary is behaving. The locked zone lies farther inward along the plate boundary, beneath the outer coast and offshore margin, where steady plate motion can be held back by friction. It is not locked in the way a door is locked. It is a region where two sides of a fault remain stuck together while the plates around them continue their slow motion. The Pacific plate keeps moving. The overriding plate is pulled and bent by that motion. Strain gathers quietly in the rock, at the surface. The land may shift by only small amounts each year, but over many decades the accumulated change becomes large enough to matter. A locked zone is identified by measurement and interpretation, not by direct sight. Scientists cannot look down through the crust and see the contact holding still. They infer its behavior from earthquake patterns, ground motion, geologic records, and physical models. Stations fixed to bedrock or stable ground can measure slow horizontal and vertical motion. If the coast moves in a way that suggests it is being dragged by the descending plate, researchers may infer that part of the interface is locked. If the same area later moves suddenly during a large earthquake, that inference can be tested against the rupture pattern. The process is careful. In Alaska, locked behavior is important because the subduction boundary has produced very large earthquakes in the past. The most powerful known Alaska earthquake in historical time occurs in the south-central region and changes coastlines over a broad area. That event shows that wide parts of the plate boundary can store strain and then release it suddenly. It does not mean that every locked patch is ready to rupture now. It means that the physical setting allows strong coupling between plates. Coupling is the degree to which the motion of one plate affects the other across their boundary. Within a locked zone, rock is under stress. Stress is force acting inside a material. It may squeeze, stretch, or shear the rock. Shear stress is especially important on faults because it acts parallel to a surface and encourages sliding. While the boundary remains stuck, shear stress can rise. The surrounding crust bends slightly. This bending is usually too small to see, but it can be measured over time. The land may move landward, seaward, upward, or downward depending on the shape of the interface and the location of the station. These small motions help define the hidden locked region. A small earthquake near a locked zone can raise attention because it may occur at a boundary between stuck and slipping behavior. faults rarely change from fully locked to freely sliding along a perfect edge. Instead, there may be transitional areas. Some patches creep slowly. Some slip in small earthquakes. Some produce slow slip events, which are episodes of fault movement lasting days, weeks, or longer without strong shaking. Slow slip can transfer stress to nearby patches. Observations indicate that such processes occur in many subduction zones. It remains uncertain how any single small quake relates to these processes unless additional measurements show a wider pattern. The locked zone also has depth limits. Near the trench, sediments and weak materials may allow slip to occur more easily, though some shallow parts can still lock or slip suddenly. At greater depth, temperature and pressure rise, and the fault may become too warm or too ductile for ordinary brittle earthquakes. Ductile rock deforms slowly without breaking sharply. Between the shallow and deeper limits, conditions may allow frictional sticking and sudden rupture. This depth range can vary from one subduction zone to another. In Alaska, the geometry changes along the margin, so the width and behavior of locked areas are not uniform. Scientists often compare small earthquakes with the edges of locked patches. An earthquake just down dip of a locked area may show where the interface begins to slip more freely, or where stress is concentrated. Down dip means farther downward along the sloping fault surface. An event up dip may occur closer to the trench. A long strike means along the length of the boundary, following the coast or arc. These terms help describe location without relying only on map directions. Once defined, they allow researchers to ask whether small events cluster near certain parts of the boundary. Concern remains cautious because earthquake systems are noisy. A cluster of small earthquakes can occur after a larger event, during background activity, or as part of ordinary adjustment. Some clusters fade, others migrate slowly, some align with known faults, while others appear diffuse because the locations are uncertain. The locked zone is therefore not judged by one tremor. It is studied through time. Instruments record wave arrivals. Analysts refine locations. Models compare observed ground motion with possible fault locking. The result is a changing picture that improves as more data arrives. The physical surface above a locked zone may offer subtle signs. Marshes, terraces, and drowned forests can record past uplift and subsidence. Tide gauges can show relative sea level changes. Satellite radar can measure small shifts in the ground when conditions allow. These records connect short-term instrument data with longer-term geologic history. They show whether the coast has moved suddenly in the past and whether it is deforming now. Still, the locked zone itself remains a buried surface. Its boundaries are estimated, not drawn with final certainty. A small quake inside or near this region may be described as concerning when it occurs where strain is already known to be accumulating. The concern is not a prediction of a large earthquake. It is a reason for closer examination. Scientists may check whether the event changes the rate of nearby small earthquakes. They may examine whether its focal mechanism matches the main plate interface. A focal mechanism is a calculation that shows the likely orientation and motion of the fault during the quake. They may compare the event with slow ground motion before and after it. The goal is to understand whether the quake is isolated slip or part of broader adjustment. At the scale of the locked zone, Alaska's quiet surface becomes the outer cover of a slow mechanical balance. The plates continue to move, but part of their boundary resists. The resistance is not permanent. It can weaken locally, creep slowly, or fail suddenly, depending on pressure, temperature, fluids, roughness, and stress history. The small earthquake is one brief release within that balance. Above it, land and sea remain calm in ordinary time. Beneath them, the locked zone holds the memory of motion not yet released, measured in small shifts, faint waves, and patient instruments. The small rupture patch is the narrower place where an earthquake actually begins and grows. It sits within the larger fault system, but it is only a limited area of contact that slips during a modest event. In Alaska, such a patch may lie on the plate boundary, within the crust above it, or inside the descending slab. Its size depends on the earthquake magnitude, the amount of slip, and the strength of the surrounding rock. A small quake does not involve the whole margin. It usually involves a compact part of a fault where stress has become large enough to overcome friction for a short time. Before rupture, the patch is held by friction. The rock surfaces are not smooth at the scale that matters. They touch at tiny high points, and those contacts carry the force between the two sides. Around the patch, stress continues to act. The surrounding fault may be stuck, creeping slowly, or already weakened by earlier movement. When the local strength is exceeded, the first slip begins at a point called the hypocenter. The hypocenter is the place inside Earth where the rupture starts. The epicenter is the point on the surface directly above it. These two words describe related places, but the rupture itself happens at depth. The first motion is small. Rock on one side of the fault moves slightly relative to rock on the other side. That movement changes stress on nearby parts of the same surface. If nearby areas are close to failure, the slip can spread outward. If they are stronger or less stressed, the rupture may stop quickly. This is one reason small earthquakes remain small. Their ruptures do not find conditions that allow broad growth. They release energy, send waves through the crust, and end. The patch then becomes part of the recorded history of the fault. The size of the rupture patch is related to magnitude, but not in a way that can be seen directly without analysis. A lower magnitude event may involve a fault area only tens or hundreds of meters across, while larger events rupture kilometers or hundreds of kilometers. The exact size depends on the stress drop, which is the difference between stress before and after the earthquake on the slipped patch. Stress drop is not always simple to estimate. Scientists use seismic waves and physical models to infer it. A small event with a higher stress drop can produce sharper waves than another small event with lower stress drop. The rupture patch also has a style of movement. In a thrust event, one side moves up over the other along a sloping surface. In a normal event, one side moves down as the crust stretches. In a strike-slip event, blocks move sideways past one another. Many Alaska earthquakes include mixed motion because the tectonic setting is complex. The style gives clues about the forces acting on the rock. A small thrust event near the subduction interface may fit the larger pattern of plate convergence. A small strike-slip event may instead belong to faults in the upper plate that accommodate sideways motion. Scientists study the waves from a small rupture patch to estimate its depth and motion. The first arriving waves compress and expand the rock as they travel. Later waves shake the ground side to side or up and down. Their arrival times, directions, and strengths are compared across stations. A small event recorded by many instruments can be located with much greater confidence than one recorded by only a few. In Alaska, instrument coverage is strong in some regions and sparse in others, because the land is large, remote, mountainous, icy, and difficult to maintain. This affects how clearly a small patch can be resolved. The rupture patch may occur on a fault that has slipped before. Many faults carry repeated small earthquakes over time. Some events repeat in nearly the same place with similar waveforms. These repeating earthquakes can indicate a small patch that slips again and again. perhaps surrounded by fault areas that creep. In other cases, a small quake may be part of a temporary cluster. The patch breaks once, nearby patches respond, and the activity fades. Observations indicate that both behaviors occur in active tectonic regions. It remains uncertain which pattern applies until the sequence is followed carefully. A small rupture patch can also alter stress around itself. The change may be slight, but nearby faults can be sensitive if they are already close to failure. Stress can increase in one direction and decrease in another. This redistribution helps explain why aftershocks often occur around the edges of a rupture. In a small quake, the affected area is limited, yet it can still produce a small cloud of related events. Scientists do not treat every aftershock as a sign of growing danger. They use the pattern to outline the patch and understand how the local fault network responds. The concern raised by a small Alaska quake often depends on whether its rupture patch lies in a significant position. If it occurs near the edge of a locked zone, it may show that stress is concentrated there. If it lies within an area that has been unusually quiet, it may draw attention as a new signal. If its mechanism differs from nearby events, it may suggest motion on a different fault. None of these interpretations become certain from the event alone. The patch must be placed within the larger map of known faults, plate motion, and recent seismic activity. At the patch scale, the earthquake is no longer an abstract point on a map. It is a physical slip between rough rock surfaces under pressure. The movement may be only a few millimeters or centimeters, but it happens quickly enough to send energy outward as waves. The surrounding rock receives that energy and carries it through layers with different speeds and strengths. Some waves travel upward to the surface, some travel deeper and outward. Instruments turn the motion into records that can be compared, filtered, and studied. The small rupture patch is therefore the first truly inner region of the quake itself. It is smaller than the coast, smaller than the arc, smaller than the locked zone, and smaller than the mapped fault. It is the exact place where stored strain becomes sudden movement. The patch does not reveal the whole future of the system. It reveals one completed act of slip. In the calm language of measurement, that act has a location, a depth, a magnitude, a mechanism, and a relation to the rock around it. Beneath Alaska's wide surface, the patch breaks, settles, and becomes quiet again, while instruments preserve the brief motion as a small but meaningful trace of the fault's continuing life. The aftershock field surrounds the small rupture patch as a shifting pattern of additional earthquakes that follow the initial slip. These events are usually smaller than the first quake, though in some sequences one event may be similar in size to another. The field is not a simple ring. It is a cloud of activity that outlines how stress has changed in the rock after the first movement. Each aftershock is a separate rupture on its own small patch, but together they reveal the structure and condition of the faulted region. Aftershocks occur because the first rupture does not leave the surrounding rock in a uniform state. Stress increases in some areas and decreases in others. Where stress increases and the rock is already near failure, additional slips can occur. These slips release energy in smaller increments. The timing of aftershocks is not regular. Many occur soon after the main event, then the rate decreases over time. This decay in activity follows a general pattern observed in many earthquake sequences, though the exact rate varies with location and conditions. In Alaska, aftershock fields are influenced by the complex geometry of faults and the wide range of depths at which earthquakes occur. A small rupture on the plate boundary may be followed by aftershocks, both on the interface and in nearby crustal faults. A small rupture within the descending slab may produce aftershocks along fractures inside the plate. The depth and location of the first event help guide expectations, but the observed pattern must be measured directly. Instruments record each event's waves, and analysts refine their positions to build a clearer image of the field. The size of the aftershock field is related to the size of the initial rupture. A modest event produces a compact field, often extending only a short distance from the original patch. Within that space, the distribution of aftershocks can show the shape of the fault that slipped. If the rupture occurred on a planar surface, the aftershocks may align along a line or a narrow band. If the fault is irregular or branching, the pattern may appear more diffuse. Uncertainty in location can blur the image, especially where station coverage is limited, but careful analysis can still reveal trends. Time is an important part of the aftershock field. The first hours and days often show the highest activity. As time passes, the number of events decreases, though occasional clusters can still occur. This decline reflects the gradual relaxation of stress around the rupture. It does not mean the region returns to its original state. The stress field has changed, and some parts of the fault may now be closer to or farther from failure than before. Observations indicate that aftershock sequences can last from days to months, sometimes longer, depending on the size of the initial event and the properties of the surrounding rock. The aftershock field can also show migration. Events may appear to move in a particular direction over time. This movement can be caused by stress transfer, fluid movement, or slow deformation along the fault. Migration is not always present, and when it is, its cause may not be clear from the seismic data alone. Scientists compare aftershock patterns with other observations, such as changes in ground motion or known fault structures, to interpret these shifts. It remains uncertain in many cases whether migration reflects a deeper process or a local adjustment. In coastal and offshore Alaska, aftershocks may occur beneath the ocean, where direct observation is more difficult. Seismic stations on land record the waves, but distance and geometry can limit precision. Where ocean bottom instruments are available, they improve the picture by capturing signals closer to the source. These instruments are placed on the seafloor and record ground motion beneath the water. Their data help reduce uncertainty in depth and location, especially for shallow offshore events. Even with such tools, some parts of the aftershock field remain less well defined than others. Aftershocks are also influenced by the materials around the fault. Rock type, temperature, pressure, and fluid content all affect how stress is released. In sediment-rich areas, aftershocks may be more scattered due to weaker, more deformable material. In stronger crystalline rock, they may align more clearly along defined fractures. Fluids within the rock can reduce friction and allow small slips to occur more easily. These effects are subtle and often require detailed study to identify, but they contribute to the overall pattern. The presence of aftershocks does not imply that a larger earthquake is imminent. They are a normal part of the earthquake process. Their main value lies in revealing the structure of the rupture and the surrounding fault network. By mapping their distribution, scientists can estimate the orientation of the fault, the extent of the slipped area, and the regions where stress has increased. This information helps refine models of the fault system and improves understanding of how the region responds to stress. In Alaska, where the tectonic setting is active and varied, aftershock fields from small earthquakes are common. Each sequence adds to a growing catalogue of events that can be compared over time. Patterns emerge when many sequences are studied together. Some areas show repeated clusters in similar locations. Others show more scattered activity. These patterns help identify persistent features in the crust and along the plate boundary. They also help distinguish between ordinary background seismicity and changes that may require closer attention. The aftershock field is therefore a dynamic extension of the initial rupture. It is not separate from the first event but part of the same process of stress adjustment. The field evolves as the rock responds to the change introduced by the initial slip. It provides a map, drawn in small increments, of how the fault system behaves at a fine scale. Each aftershock marks a point where the rock has shifted again, releasing a small amount of energy and adding detail to the pattern. Beneath Alaska's surface, this pattern unfolds quietly. The land above may remain still, with no visible sign of the activity below. Instruments record the motion, turning it into data that can be analyzed and interpreted. The aftershock field becomes a tool for understanding the hidden structure of the fault and the way stress moves through it. It is a subtle and ongoing process, one that continues until the system settles into a new balance, shaped by the initial rupture and the many small adjustments that follow. The crustal fault network lies within the overriding plate, above the deeper subduction boundary, where Alaska's outer rock shell is broken into many zones of weakness. These faults do not all have the same length, depth, or style of motion. Some extend for hundreds of kilometers across mountains and valleys. Others are short, hidden beneath sediment, forest, ice, or shallow water. Together they form an inner network that responds to the broad pressure of plate convergence, sideways motion, uplift, and local changes in load. A small earthquake may occur on one of these faults rather than on the main plate boundary, and that difference matters for how scientists understand it. The crust is the solid outer layer of Earth, but it is not a single unbroken cover. In Alaska, it is shaped by terrains, which are blocks of crust with different origins that have been joined to the continent over geological time. Some terrains began as island arcs, ocean fragments, or pieces of older margins before they were carried northward and added to Alaska. Their boundaries may remain as weak zones. Under stress, these inherited lines can move again. A small quake within the crust may therefore occur on a structure that is ancient in origin, but still active under present forces. Crustal faults can move in several ways. Strike-slip faults allow blocks to slide sideways. Thrust faults shorten the crust by pushing one block over another. Normal faults form where rock is pulled apart and one side drops downward. In Alaska, these motions can occur close together because the region is affected by both direct compression from the plate boundary and sideways escape of crustal blocks. The surface expression may be a valley, a line of springs, a straight river segment, a steep mountain front, or no clear feature at all. Many active faults are difficult to see, especially where vegetation, snow, glacial deposits, or young sediment cover the bedrock. A small quake in the crustal fault network may raise concern if it occurs near a known active fault, near infrastructure, or in an area where recent activity appears unusual. Its magnitude may be modest, yet its shallow depth can make it more noticeable than a deeper event of similar size. Shallow earthquakes release energy closer to the surface, so their shaking can be stronger near the epicenter. Even then, most small shallow events cause little or no damage. Their scientific value lies in the way they reveal which faults are moving and how stress is distributed through the upper plate. The Denali Fault is one of Alaska's major crustal faults, extending across the state in a broad arc. It is known for large strike-slip motion, where crustal blocks move mainly sideways past one another. Other important faults cross south-central Alaska and the interior, each with its own history and motion. These large faults are part of the regional framework, but small earthquakes also occur on minor faults that may not be mapped at the surface. The earthquake catalogue can therefore reveal hidden structures. When many small events align along a plane or narrow band, they may identify a fault that has not been clearly recognized before. The upper crust responds to stress in a brittle way. Brittle means that rock breaks or slips suddenly rather than flowing slowly. This behavior is most common at lower temperatures and pressures near the surface. As depth increases, pressure and temperature rise, and rock may become less likely to fracture sharply. The depth range of crustal earthquakes depends on rock type, heat flow, and fluid conditions. In many regions, most crustal earthquakes occur within the upper tens of kilometers. In Alaska, local differences in temperature and structure create variations from one area to another. Fluids can influence crustal faults. Water may move through fractures, pores, and mineral boundaries. It can come from rain and snowmelt near the surface, from deeper metamorphic reactions, or from fluids released by the descending plate. Metamorphic reactions are mineral changes caused by pressure and temperature. When fluid pressure rises in a fault zone, it can reduce the effective normal stress, which is the clamping force that holds fault surfaces together. Lower effective clamping can allow a fault to slip more easily. Scientists consider fluid effects carefully, but they do not assume them unless evidence supports the interpretation. The crustal network also responds to surface changes. Glaciers add and remove weight from the crust. When large ice masses thin or retreat, the land can rebound upward. This rebound changes stress in nearby faults. The effect is generally gradual, but in regions with rapid ice loss it can become an important part of the local stress field. Alaska's glaciers have changed significantly in many areas during the modern warming period. Observations indicate that unloading from ice loss can affect fault stress in some settings. It remains uncertain how much it influences any single small earthquake without detailed local modelling. Small earthquakes within crustal faults can occur as isolated events or as swarms. A swarm is a group of earthquakes close in time and space without one clearly dominant main event. Swarms can arise from stress changes, fluid movement, or complex fault interactions. They are common in some tectonic and volcanic regions. A swarm does not necessarily mean a large earthquake will follow. It does, however, invite close study because it shows that a local part of the crust is adjusting repeatedly. Scientists examine the depth range, migration, mechanisms, and relation to mapped structures. At this inner crustal level, concern becomes more local. A small quake beneath a remote mountain area may be mainly a scientific signal. A similar quake beneath a town, road corridor, pipeline route, or dam may receive greater practical attention because shallow faults can affect built environments. Hazard assessment depends not only on one event, but on the long-term behavior of the fault, the expected shaking from possible larger events, the nature of local soils, and the resilience of structures. Small earthquakes help refine these assessments by improving maps of active faults and revealing how frequently they move. The crustal fault network is therefore a web of hidden surfaces inside Alaska's upper plate. It carries the imprint of ancient assembly and present-day pressure. It receives stress from the subduction boundary, from sideways motion, from mountain building, and from changing ice loads. A small earthquake in this network is a brief movement on one small part of that web. It may be ordinary background activity, or it may mark a place scientists choose to watch more closely. Above it, the land may show no change. Within the crust, however, the event becomes another measured point in the slow adjustment of broken rock under steady force. The deep plate slab lies below the crustal fault network, where the oceanic plate has already passed beneath the margin and continues downward into warmer and denser parts of Earth. In this region, the plate is no longer a flat ocean floor approaching Alaska. It is a tilted body of cold rock sinking through the upper mantle. Its outline is traced by earthquakes that form a dipping band beneath the coast, the mountains, and the volcanic arc. These deeper events show that the slab remains strong enough in places to break or slip, even after it has descended far below the surface. The slab is made of oceanic lithosphere, which includes the crust of the Pacific Plate and the colder uppermost mantle beneath it. Lithosphere is the rigid outer layer of Earth. It is stronger and cooler than the surrounding mantle through which it descends. Because the slab is colder than the mantle around it, it can hold stress at depths where ordinary warm rock may deform more slowly. This temperature contrast helps explain why earthquakes can occur deep within a subducting plate. The rock remains brittle or partly brittle enough to fail, even under great pressure. As the slab sinks, it bends and stretches. Its upper side may be under one kind of stress, while its lower side may be under another. The plate also carries old fractures created before subduction, including cracks formed at the seafloor and faults produced as the plate bent near the trench. These inherited weaknesses may be reactivated at depth. A small earthquake within the slab may therefore occur on a fracture that began long before the plate reached Alaska. The event is small in size, but it belongs to a long physical history carried downward by the plate. Deep slab earthquakes differ from shallow crustal earthquakes in how their energy reaches the surface. Their waves travel through many kilometers of rock before reaching instruments and communities. Because they begin farther down, their shaking is often felt over a wider area but may be less intense near the epicenter than a shallow event of the same magnitude. A small deep quake may not be felt at all. To scientists, however, it can still be useful because it helps define the shape, angle, and internal condition of the descending plate. The depth of slab earthquakes in Alaska varies along the margin. In some regions, the slab dips more steeply. In others, it may be shallower or more complex. Earthquake locations help outline these differences. When many events are plotted in cross-section, they can reveal a dipping zone known as a Wadati-Benioff zone, named for scientists who help describe deep earthquake patterns in subduction zones. This term refers to the band of earthquakes that follows the descending plate. Once defined, the pattern becomes a guide to where the slab lies beneath the surface. At these depths, pressure is high. Rock is squeezed from all directions. Under such pressure, open cracks do not behave the same way they do near the surface. This makes deep earthquakes scientifically important because their exact failure process is not as simple as ordinary sliding along a shallow fault. Several mechanisms are studied. One involves dehydration reactions, where minerals in the slab release water as pressure and temperature rise. This released water can weaken rock or change stress conditions. Another involves changes in mineral structure that allow sudden deformation. Observations support roles for mineral reactions and fluid release, but the details vary by depth and setting. Water inside the slab has a long path. Some of it enters the plate at the seafloor through cracks and altered minerals. As the plate descends, the water is carried in minerals rather than as open liquid in most places. With increasing pressure and temperature, some minerals become unstable and release water into surrounding rock. This process does not create empty caverns or rushing underground streams. It occurs within crystals and along tiny pathways. The released fluids can influence earthquakes within the slab and can also affect the mantle above it. At the scale of section 10, the focus remains inside the slab, where mineral changes and stress interact. A small Alaska earthquake at slab depth may raise concern if it occurs in an unusual location, at an unexpected depth, or as part of a changing cluster. It may show that stress is being redistributed within the descending plate. It may also reflect normal background activity in a region where the slab commonly produces earthquakes. Scientists compare the event with past records, nearby mechanisms, and the known geometry of the slab. A single, small, deep event rarely changes the broader hazard picture by itself, but it can improve the map of the subducting plate and help refine models of how stress is carried downward. The slab is not a smooth sheet. It has thickness, layers, bends, tears, and variations in temperature. In some subduction zones, slabs may change dip or appear segmented. Alaska's geometry is complex because the margin changes from the Gulf of Alaska toward the Aleutian chain. The direction of plate motion, the age of the oceanic plate, the roughness of incoming seafloor, and the shape of the overriding plate all contribute to this complexity. Deep earthquakes help reveal these hidden changes. Their locations are like small lamps inside the descending rock, marking where failure still occurs. Energy from a slab earthquake travels through rock with different speeds and paths. Some waves pass through the cold slab itself, where they may move efficiently. Others travel through warmer surrounding mantle and crust. This can affect where shaking is felt. It can also help scientists image the slab, because wave speeds change with temperature, composition, and structure. Seismic tomography uses many wave paths to build a three-dimensional picture of Earth's interior. Tomography means imaging by slices or paths through a body. In this context, it helps show the cold descending plate beneath Alaska. The deep slab also connects the surface earthquake system to the deeper Earth without leaving the present region. The plate that once formed ocean floor now bends and transforms under Alaska. It carries old minerals into new pressure and temperature conditions. It breaks in small and moderate earthquakes as it adjusts to sinking, bending, and internal change. A small quake inside it is not a surface crack or a coastal fault. It is a signal from cold rock descending through a warmer layer, still strong enough to fail suddenly. Above it, the crustal faults and coast remain part of the same broad tectonic system, but at this inner depth, the focus is the slab itself, sinking steadily and recording its strain in quiet pulses of seismic waves. The mantle wedge lies above the descending slab and below the crust of the overriding plate, occupying a warm inner region where solid rock can slowly flow and, in some places, begin to melt. It is called a wedge because its shape is broad and tapering, bounded below by the sloping slab and above by the base of the crust. This region is not an empty chamber. It is mostly solid mantle rock under high pressure and high temperature. Over long times, it moves slowly, almost like a very thick material responding to force, heat, and changes in composition. The mantle is the thick layer of earth between the crust and the core. In the wedge beneath Alaska and the Aleutian Arc, it receives heat from the deeper earth and water-rich fluids from the descending slab. These fluids are important because they lower the melting temperature of mantle rock. Rock can remain solid at a certain temperature when it is dry, but begin to produce melt at the same temperature when water is added. This process is called flux melting, meaning melting helped by the addition of volatile materials such as water. It is one reason volcanic arcs form above subduction zones. The mantle wedge is not fully molten. Most of it remains solid, even where small amounts of melt are present. The melt exists in tiny connected spaces between mineral grains, then may gather and move upward when conditions allow. This distinction matters because the word magma can suggest large open pools of liquid rock. But most melt generation begins as a small fraction within solid mantle. The rock changes gradually. Minerals respond to heat, pressure, and fluid. Melt forms where the conditions are suitable. The process is slow compared with an earthquake, but it belongs to the same subduction system. A small earthquake is usually not generated by flowing mantle, in the same way that shallow crustal earthquakes are generated by brittle fault slip. The mantle wedge is warmer and more ductile than the upper crust. Ductile means that rock can deform slowly without breaking suddenly. Still, the mantle wedge influences earthquakes by controlling temperature, fluid movement, and stress at the base of the crust and near the top of the slab. Its thermal structure helps define where brittle earthquakes can occur and where the fault surfaces become too warm for sudden slip. The boundary between the cooler slab and the warmer wedge is a place of strong contrast. The slab carries cold rock downward, while the wedge above it is heated and stirred. Fluids released from the slab enter the wedge and change its minerals. Some minerals take in water and become weaker, others break down as conditions change. These reactions can affect how the wedge flows and how stress is transmitted toward the crust. The details are not visible directly, so scientists infer them from volcanic chemistry, seismic wave speeds, heat flow, and laboratory experiments on mantle rocks. Seismic waves travel through the mantle wedge in ways that reveal its condition. Warmer rock often transmits waves more slowly than colder rock. Rock containing melt or water-rich minerals can also slow waves or weaken them. By measuring these effects, scientists build images of the wedge beneath volcanic arcs. In Alaska, such imaging helps connect the descending slab, the mantle wedge, and the volcanic chain at the surface. The images are not perfect pictures. They are models based on wave paths and physical assumptions. Observations indicate broad zones of altered and warmer mantle above the slab. It remains uncertain in many places how melt is distributed at fine scale. The mantle wedge also participates in slow circulation. As the slab descends, it can drag the mantle near it downward. Warmer mantle from behind or below may flow into the wedge to replace material. This flow is extremely slow by human standards, but it matters over thousands and millions of years. It carries heat, redistributes fluids, and helps maintain the conditions that feed volcanic arcs. The motion is smooth compared with fault rupture, yet it shapes the environment in which the crust and slab interact. Water released from the slab does not remain as simple liquid water over broad open spaces. At high pressure and temperature, it exists as fluid within rock, along grain boundaries, and within mineral reactions. It moves through pathways controlled by pressure, permeability, and the structure of the mantle. Permeability is the ability of a material to allow fluid to pass through it. Mantle rock may have low permeability unless melt or fractures create connected pathways. The movement of fluids can be uneven, producing regions that are more altered than others. The mantle wedge is also tied to the chemistry of volcanoes. Elements carried down by the slab can be added to the wedge and later appear in erupted lavas. By studying volcanic rocks, scientists learn about processes hidden far below the surface. Some chemical signatures show the influence of seawater-altered oceanic crust or marine sediment. Others reflect melting conditions in the mantle itself. These chemical signals help show that the wedge is not isolated. It receives material from the descending plate and returns some of that material upward through volcanic systems. For earthquake concern, the mantle wedge provides context rather than a direct warning. A small quake near the slab or crust may be interpreted partly through the temperature and fluid conditions around it. If the event occurs near the depth where the plate interface changes from locked to creeping, the thermal structure of the wedge may help explain that transition. If it occurs near a volcanic area, scientists may examine whether the quake fits ordinary tectonic patterns or whether other monitoring data indicate volcanic unrest. A single small quake is not enough to establish such a link. Multiple observations are needed. The wedge also affects the strength of the lower crust above it. Heat rising from the mantle can warm the base of the crust, making it more ductile. In warmer areas, earthquakes may be limited to shallower depths. In cooler areas, brittle failure can extend deeper. This helps explain why earthquake depth varies from place to place along active margins. Alaska's tectonic setting includes cold subducting slab, volcanic heat, thick crust in some regions, and varied structure along the arc, so the depth of earthquake activity changes across the region. At this inner level, the small Alaska quake is no longer considered only as a surface shaking event or a fault patch. It is part of a layered thermal and chemical system. Above the slab, the mantle wedge receives fluids, transfers heat, and slowly moves. It helps determine where rock is brittle, where it flows, and where melt begins. The wedge remains hidden, dense, and mostly solid, with changes that unfold slowly in the dark beneath the arc. Its role is quiet but essential. It forms the warm region between sinking plate and crust, where the conditions of earthquakes and volcanoes are shaped by heat, water, pressure, and time. Magma pathways lie inward from the mantle wedge, where small amounts of melt leave their place of origin and begin to move through hotter rock, lower crust, and fractured zones beneath the volcanic arc. Magma is molten rock that remains below the surface, usually carrying crystals, dissolved gases, and chemical elements gathered from its source. In Alaska's subduction setting, magma does not rise as one simple river. It moves in pulses, pockets, thin sheets, and connected cracks, following pressure differences and weaknesses in the rock above the mantle wedge. The first movement of melt begins at very small scale. Within partially melted mantle, liquid gathers along grain edges and connected films. When enough melt connects, it can separate from the solid rock and move upward because it is generally less dense than the surrounding material. The path is not straight. It is guided by stress, temperature, rock strength, and the openings available. Some melt may stall, cool, and crystallize before it rises far. Some may gather into larger bodies. Some may continue upward toward the crust beneath volcanoes. Each route changes the melt's composition and temperature. Beneath Alaska's volcanic arc, magma pathways are influenced by the shape of the crust. The crust may be thick in some places and thinner in others. It may contain older faults, fractures, and boundaries between different rock blocks. These structures can guide rising melt, much like cracks guide water through stone, though the conditions are hotter, deeper, and far slower. Magma may intrude into the crust as dikes or sills. A dike is a sheet of magma that cuts across rock layers. A sill is a sheet that spreads between layers. Both can cool underground without erupting. Magma movement can produce earthquakes, but not every earthquake near a volcano is caused by magma. Rock can break as magma forces open a crack. Fluids can move and change pressure. The crust can adjust to regional tectonic stress. A small Alaska quake near a volcanic area therefore requires careful interpretation. Scientists compare its depth, wave pattern, timing, and location with other signs: ground swelling, changes in gas release, changes in heat, and patterns of many small quakes may suggest magma movement. Without such supporting evidence, a single small quake remains only a small quake in a complex region. As magma rises, pressure decreases. Dissolved gases may begin to separate from the melt, forming bubbles if conditions allow. Water, carbon dioxide, sulfur compounds, and other gases can be held within magma at depth. Their behavior influences magma buoyancy and eruption potential. At the pathway level, however, much magma never reaches the surface. It may cool slowly and become intrusive rock. It may add heat to surrounding crust. It may mix with other magma. It may remain stored in a reservoir, which is not usually a single open cavern but a region of partly molten rock, crystals, and mush-like material. The term magma reservoir describes a zone where melt is stored, evolves, and sometimes moves again. In many modern volcanic systems, reservoirs are understood as crystal-rich bodies with pockets of melt rather than large empty chambers filled entirely with liquid. This view comes from geophysical imaging, studies of erupted rocks, and laboratory work. The reservoir can grow by repeated injection of new magma. It can cool and solidify. It can be recharged from below. Its pressure can change when magma enters, when gases separate, or when surrounding rock deforms. Earthquakes related to magma pathways often have particular characteristics. Some are high-frequency events caused by brittle breaking of rock. Others are longer-period events thought to involve fluid movement or resonance in cracks. Tremor is a more continuous seismic signal that can occur when fluids or magma move steadily. These signals are not interpreted in isolation. Volcano observatories study them with ground deformation, gas measurements, satellite thermal data, and field observations. In Alaska, remote volcanoes can be difficult to monitor closely, so scientists rely on networks of instruments, satellites, and careful comparison with past activity. The connection between tectonic earthquakes and magma pathways is subtle. Regional stress from the plate boundary can open or close cracks that magma might use. A larger earthquake can sometimes change pressure in volcanic systems, but responses vary widely. Small earthquakes usually produce only small stress changes. If a small quake happens near a magma pathway, it may be a response to local pressure, regional stress, or ordinary fault movement. Observations indicate that volcanic and tectonic processes can interact in subduction zones. It remains uncertain in most individual cases whether a small quake directly reflects magma movement, unless the surrounding evidence is strong. Magma pathways also carry chemical information from deeper regions into shallower crust. As melt moves, it reacts with surrounding rock, crystallizes minerals, and may mix with other melts. Each step changes its composition. Some elements enter crystals. Others remain in the liquid. Gas content changes with pressure and temperature. By studying erupted lava and ash, scientists reconstruct parts of this hidden journey. The rocks at the surface become records of pathways that existed long before eruption, though they do not reveal every detail. Heat from magma affects the crust around it. Rock close to intrusions can become altered by hot fluids. Minerals can change. Water circulating through fractures can dissolve and redeposit material. This can strengthen some zones and weaken others. Altered rock may be more likely to slide on slopes or fail during shaking. Underground, alteration can affect how cracks open and how fluids move. These effects are important in volcanic regions, but they vary greatly by location. They are studied with mapping, geochemistry, seismic data, and temperature measurements where available. At the scale of magma pathways, the small Alaska quake becomes part of a setting where heat and fracture meet. It may not be volcanic in origin, even if it lies near volcanoes. It may simply occur on a fault that cuts the crust above the subduction system. Yet the same region contains hidden routes for melt rising from the mantle wedge. Scientists separate these possibilities by using measured evidence rather than assuming a dramatic cause. The more observations agree, the clearer the interpretation becomes. The fewer observations available, the more carefully uncertainty is stated. Beneath the volcanic arc, magma pathways remain mostly invisible. They are inferred from earthquake patterns, ground motion, volcanic gases, rock chemistry, heat flow, and the shapes of past eruptions. Some pathways are active only briefly, some cool into solid rock. Some are reused over long periods. They form a branching inner system through which melt, heat, and fluids move upward in small increments. Above them, volcanoes may sleep for long spans of time, slopes may hold snow and cloud, and the surface may appear still. Below, the paths remain warm, changing and partly open, shaped by pressure, fracture, and the slow rise of molten rock through Alaska's deep volcanic crust. Rock minerals form the solid materials that hold stress, transmit waves, react with fluids, and shape the strength of Alaska's faults at smaller scales. A fault may appear on a map as a line, and a rupture may be described as a patch. But inside the rock, the behavior depends on minerals. Minerals are naturally occurring solid substances with ordered internal structures and chemical compositions. Quartz, feldspar, olivine, pyroxene, mica, clay minerals, and many others can be present in different parts of the crust, slab, and mantle. Each responds differently to pressure, heat, water, and force. In the upper crust, common rocks may include granitic bodies, volcanic rocks, sedimentary layers, metamorphic rocks, and broken mixtures along fault zones. Granitic rocks often contain quartz and feldspar. Volcanic rocks may contain feldspar, pyroxene, olivine, and glass altered by time and fluids. Sedimentary rocks may include sand grains, clay minerals, carbonates, and organic material. Metamorphic rocks contain minerals that have changed under heat and pressure. Alaska's geology is varied because its crust is assembled from many older pieces, so the mineral setting of a small earthquake can differ greatly from one location to another. Minerals matter because they control friction. A fault surface made of hard, interlocking minerals may resist sliding differently from one rich in clay. Clay minerals are sheet-like minerals that can hold water and deform easily. In some fault zones, crushed rock becomes fault gouge, a fine material produced by repeated grinding during slip. Gouge may contain fragments of the surrounding rock, newly formed minerals, and fluids trapped in tiny spaces. Its properties can determine whether a fault sticks, creeps, or slips suddenly. A small quake may begin where the local mineral mix allows stress to overcome resistance. Quartz is strong at low temperatures but can change its behavior with heat and pressure. Feldspar can fracture and alter into weaker minerals over time. Mica and clay minerals can form smooth, sheeted surfaces that may slide more readily under some conditions. Olivine and pyroxene are common in mantle rocks and respond to deeper pressure and temperature conditions. Serpentine, a water-rich mineral group formed when mantle rocks react with water, can be important in subduction settings because it may weaken rock and store water. These minerals do not act alone. They form textures, layers, veins, and mixtures that create the real mechanical behavior of rock. Water changes mineral behavior in quiet but important ways. It can enter cracks, react with minerals, and form new phases. It can weaken chemical bonds at grain surfaces. It can raise pore pressure and reduce the clamping force across a fault. It can also help minerals dissolve in one place and grow in another. These effects happen at different rates depending on temperature, pressure, and fluid chemistry. In a fault zone beneath Alaska, water may come from near-surface sources, from deep metamorphic reactions, or from the descending slab. The source matters less at the mineral scale than the way water changes strength and friction. Pressure pushes mineral grains together. At shallow depths, grains may break and slide. At greater depths, grains may deform, rotate, or change shape slowly. Temperature increases with depth and changes how minerals respond. A cold mineral grain may crack. A warmer one may bend by movement inside its crystal structure. This transition from brittle to ductile behavior is gradual. It does not happen at one exact depth everywhere. It depends on mineral type, strain rate, water content, and local heat flow. The depth of earthquakes is partly controlled by this mineral scale transition. Small earthquakes occur where rock can still fail suddenly. At mineral scale, failure may involve breaking grain contacts, sliding along tiny surfaces, crushing asperities, and weakening gouge. Asperities are small high points or stronger areas on a fault surface that carry much of the stress. When these points fail, slip can begin. The rupture then spreads if nearby contacts also fail. In a small quake, the process remains limited. Many grain contacts break or slide within the patch. But the rupture does not continue far across the larger fault. The mineral arrangement helps decide that limit. Mineral transformations inside the descending slab can also produce stress changes. As pressure and temperature increase, minerals that were stable near the ocean floor may become unstable. They may reorganize into denser forms, release water, or shrink in volume. These changes can create local stress and weaken parts of the rock. Deep earthquakes may be linked to such transformations, though the details remain studied and debated. Observations indicate that mineral reactions and fluid release play important roles in subducting slabs. It remains uncertain how each reaction contributes to any single small event. The chemistry of minerals also affects seismic waves. Different minerals have different densities and elastic properties. Elastic properties describe how a material changes shape under force and then returns toward its original form. Waves travel faster through some minerals and slower through others. Water, melt, cracks, and altered minerals can reduce wave speeds or absorb energy. When scientists image Alaska's interior, they interpret these wave changes as clues to temperature, composition, and fluids. The mineral scale therefore influences both the earthquake process and the way the process is observed. Fault rocks often show evidence of repeated movement. Some contain polished surfaces called slicken sides, where sliding has smoothed the rock. Some contain crushed fragments in a fine matrix. Some contain veins filled with minerals that grew from fluids after cracks opened. Others show layers that record many episodes of slip and healing. Healing means that a fault regains strength through compaction, mineral growth, or changes at grain contacts after movement stops. A fault that heals can store stress again. A later small earthquake may break through part of that healed zone. Laboratory experiments help connect minerals to fault behavior. Researchers place rock samples under controlled pressure and temperature, add water when needed, and force the samples to slide or deform. These experiments cannot reproduce the full size and complexity of an Alaska fault, but they reveal principles. They show how friction changes with slip speed, mineral type, grain size, and fluid pressure. They also show how some materials weaken rapidly while others strengthen. Such results are combined with field observations and seismic data to interpret natural earthquakes. At this inner mineral region, the small Alaska quake becomes a material event. It is not only a point, a magnitude, or a wave pattern. It is a change in rock made of minerals with different strengths, shapes, and reactions. Stress moves through grains. Fluids occupy tiny spaces. Contacts lock, weaken, and slip. Some minerals break sharply, others bend slowly or transform under pressure. The event begins only where the local material conditions allow sudden failure, above the mineral scale. The landscape remains large and quiet. Within the rock, the hidden details of composition, water, temperature, and pressure help decide how a small movement starts, stops, and becomes part of the measured life of Alaska's active Earth. Grain boundaries lie deeper in scale than minerals as named materials, because they are the thin contacts where one mineral grain meets another inside solid rock. A grain is a small crystal or fragment within a rock. Its boundary may be sharp, curved, rough, altered by fluid, or lined with tiny particles. These boundaries are narrow, but they control much of the way rock holds stress and changes shape. In an earthquake system, the large motion of a fault depends partly on what happens at these small contacts, where pressure, friction, water, and mineral surfaces meet. Inside a fault zone, grains are rarely arranged in a simple pattern. Some are large fragments broken from older rock. Some are fine particles produced by crushing during earlier slip. Some are flat and sheet-like, especially where clay or mica is present. Others are angular, hard, and interlocked. Between them are pores, cracks, films of water, and places where new minerals grow. The whole material may look solid from far away, but at grain scale it is a crowded structure of contacts and spaces. When stress acts on the fault, force is carried through the structure along many small pathways. The strength of the rock depends on how these grains touch. If grains are tightly pressed together, friction may be high. If they are separated partly by fluid pressure, the effective grip may be lower. If grains are angular and locked, they may resist movement until they break. If grains are smooth or coated with weak minerals, they may slide more easily. A small earthquake begins when enough of these contacts fail within a patch, allowing one side of a fault to move. The process is very fast at human scale, but it is built from many tiny failures at grain boundaries. Friction at grain boundaries is not constant. It can change with slip speed, pressure, temperature, and the history of contact. Some materials strengthen when they sit still, because grain contacts grow, compact, or bond over time. This is called healing. When sliding begins, those contacts may weaken. Other materials may become stronger as they slide, resisting continued movement. These behaviors help determine whether a fault creeps slowly or slips suddenly. In the setting of a small Alaska quake, the grain boundary behavior helps decide why motion starts on a limited patch and why it stops rather than spreading farther. Grain size matters. Fine-grained fault gouge can behave differently from coarse broken rock. Smaller grains create more surface area, which gives fluids and chemical reactions more places to act. Fine material can compact tightly, hold water, or form smooth zones that localize slip. Coarser material may lock more strongly but can break into smaller pieces during movement. Repeated earthquakes can grind grains smaller over time, changing the fault's properties. Between earthquakes, minerals may grow again in pores and cracks, partly healing the zone and preparing it to store stress once more. Water at grain boundaries is especially important. It may occur as thin films, fluid in pores, or water held within minerals. Even a small amount can change how grains slide and react. Water can reduce friction by raising pore pressure. It can also promote chemical reactions that form weaker minerals. In some conditions, water helps pressure solution, a process in which stressed mineral surfaces dissolve slightly and material moves to places of lower stress. This can allow slow deformation without sudden rupture. In other conditions, fluid pressure can make sudden slip easier. The effect depends on the local balance of pressure, temperature, permeability, and mineral composition. Temperature changes grain boundary behavior as well. Near the surface, colder grains tend to break or slide in a brittle way. At greater depth, warmer grains can deform through processes inside crystals and along boundaries. They may slowly change shape, rotate, or allow atoms to move from one site to another. This helps rock flow rather than fracture. The transition is gradual, within Alaska's active margin. Some rocks remain cold and brittle because the descending slab carries low temperatures downward, while other regions are warmed by the mantle wedge and volcanic systems. At grain scale, these differences decide how easily sudden failure can happen. During an earthquake, the slipping surface may become very thin. Motion can concentrate into a narrow band of crushed grains, sometimes only millimeters or centimeters thick. Within that band, grain boundaries experience rapid shear. Shear means movement in which adjacent parts slide past one another. Rapid shear can produce heat, break grains, increase fluid pressure, or create temporary weakening. In large earthquakes, these effects can be extreme. In a small quake, they are more limited. But the same basic physics applies. The fault patch weakens enough to slip, then strengthens or meets stronger surroundings and stops. The stopping of a small rupture is as important as its beginning. At grain boundaries outside the slipped patch, conditions may not support continued motion. Contacts may be stronger, fluid pressure may be lower, the stress may be less concentrated. The fault may bend into a rougher shape. These barriers can halt the rupture. Some barriers are temporary and may fail in later events. Others persist for long periods and help divide a fault into smaller segments. Scientists infer these barriers from earthquake patterns, rupture sizes, and repeated activity. But the controlling details often lie at grain scale. Grain boundaries also influence the waves that leave the rupture. When grains break and slide, they release energy in a range of frequencies. Rougher, stronger contacts may produce sharper high-frequency waves. Smoother or more gradual slip may produce lower frequency signals. The recorded waveform therefore carries indirect information about the fault material. It does not reveal each grain, but it reflects the combined behavior of countless contacts. Laboratory experiments on powdered rock and fault gouge help connect these signals with possible grain-scale processes. At this scale, uncertainty remains natural. No instrument can watch every grain boundary inside an Alaska fault during a quake. Scientists use experiments, theory, drilling samples where available, exposed ancient fault rocks, and seismic records to build a careful picture. Observations indicate that grain size, fluids, mineral coatings, pressure, and temperature strongly influence fault slip. It remains uncertain exactly which contacts fail first in a natural small earthquake, because the source lies hidden within rock and the process completes quickly. The grain boundary region is therefore a quiet inner world of contact and change. It contains no open space like a cavern and no simple smooth plane. It is a packed fabric of crystals, fragments, pores, fluids, and tiny surfaces under pressure. A small Alaska quake, when viewed at this scale, is the rapid rearrangement of these contacts inside a limited fault patch. The movement is brief, but it reflects a long preparation grains pressed together, weakened by water, altered by minerals, healed by time, and stressed again by plate motion. Far above, mountains, coasts, and islands keep their slow forms. Deep inside the rock, the smallest surfaces decide when solid ground can suddenly slip. Atomic strain lies at the deepest inner level of the earthquake process, beneath grains, beneath minerals, beneath faults and plates, where the behavior of rock is governed by the arrangement of atoms and the forces that bind them. At this scale, rock is not seen as a solid block, but as a structure made of atoms linked in ordered patterns called crystal lattices. Each mineral has its own lattice, with atoms arranged in repeating units. The strength of a rock arises from the bonds between these atoms, which resist being stretched, compressed, or shifted. Strain at the atomic level begins when forces act on these bonds. In a tectonic setting, such as Alaska, stress applied over large distances is transmitted through rock down to this smallest scale. Bonds between atoms are slightly stretched or compressed. These changes are extremely small in distance, but they occur throughout the material. When many bonds are affected together, the rock as a whole deforms. If the deformation remains within limits, the rock can return to its original state when the stress is removed. This behavior is called elastic deformation. Elastic deformation stores energy. The energy is held in the strained bonds, much like tension stored in a compressed spring, though the analogy remains imperfect because atomic bonds behave according to quantum mechanical forces rather than simple mechanical parts. As stress increases, the amount of stored energy grows. At the same time, imperfections within the crystal lattice play a role. No natural crystal is perfect. There are defects such as dislocations, vacancies, and substitutions. A dislocation is a line defect where the regular pattern of atoms is interrupted. These defects allow parts of the lattice to move under stress without requiring all bonds to break at once. At lower temperatures and higher stress, the movement of dislocations may not be enough to relieve strain smoothly. Bonds can reach a point where they break. When many bonds break and reform in a coordinated way, a crack can form or a fault surface can slip. At the scale of a small earthquake, this process is concentrated within a rupture patch. The macroscopic slip observed at that patch is the combined result of countless atomic scale changes. Bonds break, atoms shift positions. New bonds form, and energy is released as vibrations that propagate outward as seismic waves. The transition from stable strain to sudden failure depends on how bonds respond to increasing stress. Some bonds may break earlier due to local conditions such as impurities, defects, or stress concentration. When one bond breaks, it redistributes force to nearby bonds. If those bonds are already close to their limits, they may break as well. This can create a cascade, where failure spreads through a region. In a small quake, the cascade is limited. It does not continue across a large fault. It remains confined to a small area where conditions allow rapid bond failure. Temperature influences atomic behavior. At higher temperatures, atoms vibrate more and can move more easily within the lattice. This can allow deformation to occur without sudden failure, as atoms rearrange gradually. At lower temperatures, atoms are more fixed in place, and bonds are more likely to break suddenly under stress. In Alaska's subduction setting, cold conditions carried by the descending slab allow brittle behavior at greater depths than would otherwise be expected. This means atomic bonds can store and release energy suddenly deeper in the Earth than in warmer regions. Pressure also affects atomic strain. High pressure pushes atoms closer together, increasing the force required to change their positions. However, pressure can also stabilize certain mineral structures, making them more resistant to change until a threshold is reached. When that threshold is exceeded, the release of energy can be abrupt. In some cases, changes in mineral structure at high pressure can contribute to deep earthquakes. These processes involve rearrangement of atoms into new configurations, accompanied by a release of stored energy. Fluids influence atomic interactions by altering the chemical environment at grain boundaries and within minerals. Water molecules can weaken bonds by interacting with atomic structures, especially at surfaces and defects. This can lower the stress required for bond breaking and facilitate slip along faults. At depth, water is often present within minerals rather than as free liquid, but its release during mineral transformations can affect local conditions. The exact role of fluids at atomic scale is complex and remains an area of active study. Seismic waves generated by an earthquake are the outward expression of atomic strain release. When bonds break and reform rapidly, they create vibrations that travel through the lattice. These vibrations move as waves, carrying energy away from the source. The speed and form of these waves depend on the properties of the material, which in turn depend on atomic arrangement and bonding. Thus, the signals recorded by instruments at the surface are ultimately rooted in processes occurring at the scale of atoms. Uncertainty remains at this deepest level, while laboratory experiments and theoretical models provide insight into atomic behavior. Direct observation of bond breaking during natural earthquakes is not possible. Scientists rely on indirect evidence, combining seismic data, rock samples, and physical principles. Observations indicate that atomic-scale processes control the initiation and propagation of rupture. It remains uncertain how these processes vary in detail from one earthquake to another, especially in complex natural settings like Alaska. The small Alaska quake, when viewed at this scale, is no longer a movement of plates or faults alone. It is the release of energy stored in atomic bonds, built up over time by slow tectonic forces. Each bond that breaks contributes a tiny amount to the total energy released. Together, they create the motion detected by instruments and sometimes felt at the surface. The event is brief, but it reflects a long accumulation of strain at the smallest level of matter. Above this scale, grains, minerals, just faults, and plates organize the behavior into larger patterns. At the atomic level, the process is continuous with the larger structure but governed by fundamental interactions. The bonds hold, stretch, and finally give way, allowing the rock to adjust. In this way, the deepest inner region of the earthquake process connects directly to the broad landscape of Alaska. The quiet surface, the shifting coast, the hidden slab, and the small rupture patch all depend on the same basic forces acting at the level of atoms, unseen yet essential to the motion of the Earth. The narrative settles into a slower rhythm as the layers of Earth return to stillness. The wide landscape of Alaska remains quiet under its sky, with mountains, coasts, and ocean holding their steady forms. Beneath that calm surface, motion continues, though now it is slow and continuous rather than sudden. Plates keep moving at a pace too small to notice in a single day. Strain builds again in rock, carried from the scale of continents down to the scale of atoms. The small quake becomes part of the past, its waves absorbed into the earth and recorded only in instruments and memory. Its rupture patch has slipped and come to rest. The aftershock field fades, faults settle into a new balance, the deep slab continues its descent, the mantle wedge continues its quiet flow. Magma pathways remain hidden, carrying heat and material upward in slow increments. Minerals adjust, grain boundaries hold, and atomic bonds bear the gentle pressure of ongoing motion. Uncertainty remains, as it always does in the study of Earth. Observations provide patterns, models suggest explanations, and measurements improve understanding, yet the exact timing and place of future earthquakes remain unknown. This uncertainty is not a sign of disorder, but a reflection of the complexity of natural systems. Scientists continue to observe, measure, and refine their understanding with patience. Above all of this, the surface world rests. Snow covers ridges, water moves along coasts, air drifts across valleys and islands. Life continues without awareness of the small adjustments below. The Earth does not rush. Its movements are measured in long spans, interrupted by brief moments of release. The small Alaska quake is one such moment, now complete. The mind can rest with this steady view. Beneath the quiet landscape, processes continue in balance, guided by forces that are constant and gradual. The Earth holds its shape, changes slowly, and releases strain when needed, then returns to calm. In that calm, the motion becomes gentle again, and the deep system settles into its slow, continuous rhythm.